Welcome to Aerospace Structure 2. We'll be covering composite overwrapped pressure vessels, which in this particular course, we're going to cover particular types of structures that tend to be quite challenging. Composite overwrapped pressure vessels is one of them. Another one is bellows, for example, sandwich structures, certain types of structures that tend to give problems. And so composite overwrapped pressure vessels is a very advanced technology that's complicated and is used extensively in all kinds of industry, including automotive, natural gas vehicles, for example, is used in aircraft, is used in launch vehicles, spacecraft, and many other applications across the world. And so it is a technology that's quite leveraged. Let's first try to introduce you to a paper that I suggest for you to read. The paper was written in 2011 by Pat Scott Forth and Lori Grimes Ledesma, who I consider experts in the arena. It's a NASA SP 2011 document that I really suggest that you go through and read, and it will be part of the reading as well. So you're kind of forced to go through that. A composite overwrapped pressure vessel is a technology that has been developed for many years. It's not new technology, but it presents challenging aspects in terms of design verification and test verification. However, as more maturity, as this technology achieves more and more maturity, this technology is becoming a little bit easier and easier to size early and close the design at the end. And it works really well. The use of composites is quite extensive. In the 1960s, there's, that's Apollo, right? Pre-composites. But 1970s, you start to have some composite pressure vessels. The composite wing leading edge was composites. 1990s, you're looking at International Space Station incorporating composite pressure vessels. Today, the Orion has composite pressure vessels. The SLS system has composite pressure vessels. Almost everything now has composite pressure vessels, which is a quite significant achievement because composites can reduce weight. They can reduce, they may be costly, but they can also reduce weight, is the idea here. And you can tailor them to give the best performance you want for any given application. So what is a composite overwrapped pressure vessel? What is it? So this course is not a composites course. I teach a different composites course, and you can watch some of the content in my YouTube channel or take a course in person with me. Regardless, a composite structure is one, and it's not defined here, but composite structure is a composite material that uses two or more constituents that have different microstructure. For example, one of the constituents will be fiber, and the other constituent will be a matrix material and a binder typically. And this fiber matrix system, the fiber provides the reinforcements to the matrix, kind of like reinforced concrete. In the reinforced concrete, you have these bars going through the concrete. Those bars are taking the axial loads, while the resin is taking other types of loads, more to keep the fibers in place, if you will, or the reinforcements in place. That is the goal of the matrix here. The matrix gives it the shape that you see. Like without the matrix, I will not be able to shape into cylinder. Secondly, the matrix provides the binding so that it can transfer loading from one fiber to adjacent fiber. So it's acting as a conglomerate of material that provides cohesiveness on how the structure efficiently takes these loads. The composite tends to be of a fiber system such as carbon. Doesn't have to be, but it can be. And the resin can be like an epoxy, as an example. In the case of a composite overwrapped pressure vessel, the fibers typically tend to take most of the load. And I'll show you later that most of the analysis even ignores the effects of the resin because the fibers take most of the load. The fibers are usually wrapped around a cylinder. And we're going to be using a technology called the filament winding composites. We're going to be winding a composite structure. That's the idea there. And as we wind it, we're forming the COPV. That's the idea behind this. And the fibers will run from one boss to another. So this one boss, one polar boss, to the other side. And these fibers could also stop at the tangent point. So for example, here, you can see that this is a cylinder portion and this is a dome portion. So What I'm calling tangent is the location where the cylindrical section ends, and then you have this dome section start. Well, you could have fibers that run up to this point and stop, for example. That can happen. But a lot of the helical angles, a lot of the ply angles that are not at 90 degrees can run from one boss to another, for example. A metallic liner is typically used in COPV as a fluid permeation barrier. There are liners that are used also that are not metallic. So non-metallic liners do exist. The purpose of this liner, so if you look at a composite structure is a matrix material that's embedded within the fiber, right? And so that matrix material tends to be porous, usually. And so if I pressurize that matrix composite material that's fiber reinforced, say up to 5,000, 10,000 psi, that amount of pressure is going to cause leakage through the wall because the matrix composite tends to be, quite porous. As a consequence, the idea there then with composite overwrapped pressure vessels is to provide a liner, something like a metallic liner that provides a barrier so the leakage cannot occur through the wall. That's the idea. It's a fluid permeation barrier. But it doesn't have to be metallic liners, what I'm saying. It could be non-metallic. That exists also. These fluid retention barriers work really well. These liners serve to maintain acceptable leak rates, and it doesn't affect the fluid purity at all. You don't want a material for the liner that has chemical compatibility issues with the fluid you're working with. Secondly, you don't want to have a situation where you're adding impurity to the fluid, which could be a problem for this propulsion system. Okay, so yeah, you can see here that it's a very interesting idea. It's not, mind-bending or anything, but again, the composite overwrapped pressure vessel, the goal of that outside exterior, the composite itself, the goal of that is to take the high pressure loads, while the inner liner is there to be a barrier for you. And again, like I said, COPVs are used extensively across all applications, even Department of Transportation applications. The composite overwrapped pressure vessels have a significant weight advantage over all metal vessels. That's the bottom line. But as compared to all metal vessels, COPVs do require unique design, manufacturing, and test requirements, and we'll be covering some of that today. Okay, we'll be covering some of that today. Okay, so what we're really talking about here is COPVs, which are used in extensive applications. And the purpose of them is to store fluid at high pressure to be used in a propulsion system. That is the purpose. And so you may design the port size, for example, for particular flow rates, as an example. That could drive that design. The bottle size depends on how much fluid you want to store. You can store fluid using 10 of those, or you can design it using a large one that encompasses 10 of those. You have to look at the trades and what's best for you for your particular application, right? Yeah, so with that said, I want to play a short video. So let's look at a video of the manufacturing of a composite overwrapped pressure vessel, see how that looks. so the thing I want to point out here is the fibers are placed, so the fibers are in a spool, and then they're fed in through a resin bath, the matrix material basically, which is fluid. And as the resin flows through the fibers, now that fiber is placed onto the mandrel. We call that mandrel. In this case, the mandrel is a liner. And it's getting wrapped around back and forth at different ply angles. So you can, because you want to tailor composite to give you the best performance. So there'll be different ply angles. And then finally, the composite here, which is going to be, we call it filament wet winding. So it may be wet winding. You will then take this composite and place it in an autoclave, which will then be heated up, and on the pressure, it will be cured. It will cure to form the polymeric links within the resin. So that's the approach that's used for composites manufacturing. Um, and so COPV involve a much more complex mechanical understanding due to the interplay between the composite overwrap and the inner liner. If there's no inner liner, it'll be much easier analysis. The liner design concepts and requirements have been borrowed from the metal vessel community. However, the application of metallic vessel design standards to a very thin liner, especially the composite, is not straightforward. Okay, because what you have here, this liner material is very thin, extremely thin. And so as a consequence, it makes this very complex. Different failure modes exist as a consequence for COPVs compared to all metal vessel designs. And we need to understand these failure modes as it is much more complicated than metal vessels. So a little bit of history. In the early 1970s, there was a technology transfer task that basically looked at improving respiratory protection for municipal firefighters. And that task eventually led to the widespread commercialization of COPVs. That's how it kind of started. The NASA Firefighters Breathing System program that arose from this assignment really quickly evolved into a significant technology effort involving a cooperation between NASA and many different organizations across the United States. That breathing system was commonly employed in the 1970s using a more conventional aluminum design or steel. While these vessels met appropriate DOT standards, and we're talking about very high pressures here, okay, 2,200 psi. These requirements were not really optimal for the reduction in physical dimensions. You know, to achieve a reduction, and to improve the system, the air storage was in the 4,500 psi range. So more on the COPV history. To some extent, the success of the 1970s that we had on the COPVs, of these firefighter COPVs, really helped, really kind of helped a lot to space programs, because we then had the use of Kevlar COPVs for the storage of large quantity of high pressure of helium and nitrogen. And they had four helium and nitrogen in the space shuttle program. You can see them pictured here. And at this time, metal vessel design and test standards had dominated. So the new standards didn't really support COPV performance characteristics. And so they had to come up with ways to address COPVs. A lot of testing was done. A lot of development testing was done, with a primary emphasis on making sure that we have a good understanding of the load sharing between the liner and the overwrap. And which is, overwrap is really, let me make sure it's understood. Let me ask this question. The question is, what takes more load, the liner or the overwrap in this design? So the answer to that again is that the fibers take most of the load. Liner is there to protect it. So, but you still have some load going into the liner because it's not, trivial. So you have to really address it. So the COPV design requires an analysis of the liner, fiber overwrap, and the interaction of the two. COPV liners may be of ductile materials such as soft aluminum with only minimal load sharing capabilities. High strength steel, Inconel, titanium, or cryogenically formed stainless steel may be alternately be used, and it can result in a load sharing of the liner. And I want to point that out, that a lot of different materials are used. they try to go for ductile materials. We don't want to have a brittle material because um, that will defeat the purpose of having a liner there that acts like a barrier. The fiber is generally applied as a ribbon of multiple fibers, like I talked to before, that goes through the resin. You saw it in the video there, although it was a fast forward video. Um, and yeah, and so that's the goal there. The pressure vessel liner and the dispensing head for the fiber ribbons move in relation to one another. And what that does, as the machine is moving, is laying down the fibers at a particular fiber orientation and achieving a particular pattern design that you want. If the vessel is cylindrical rather than spherical, the fiber winding will be a little bit different. It's normally applied in both the helical and hoop orientations with almost equal amounts of fibers going in each direction. While in a pressure vessel that's cylindrical, you're going to have more fibers oriented towards the hoop direction because you're going to have a lot of pressure acting on that cylinder, which is going to cause a lot of hoop stress in that direction. The winding process consists of multiple critical steps. You have to really hone in into the resin content. You need the fiber configuration, winding tension, and the pattern of the wrap in relation to the axis of the liner. So a lot of things need to be considered during development. You may have to do several tests or several windings to figure which combination of this will result in the best design. The resin is then allowed to cure. You let it cure at an elevated temperature, like I said before. And curing really means drying and hardening. You're trying to dry the resin and harden it. And what we're doing in that process, we're trying to build those polymeric links within the resin that allows the composite to be one entity, right? And we want to decrease the number of voids possible there. So that's part of what we're doing. So looking at what we're talking about here, the process is quite complicated. So let's look at the COPV, something I call autofrettage. We'll be covering that a bit. It's also discussed in that paper I talked about. So what is autofrettage? I'll explain it. So when you cure the composite, you wrap the fibers onto the liner. And when you put that composite into the autoclave, because the coefficient of thermal expansion of the composite system tends to be an order of magnitude lower typically, or less than that of the liner, what ends up happening is that the liner expands in that process a little bit. So you're going to have some amount of expansion of the liner due to the CT mismatch. But after it cools down, the liner will pull back a little bit. Now, that's going to introduce some stresses between the liner and the overwrap. So what ends up happening that is that between the liner and overwrap, you could have an adhesive system, something that glues them together. That's one approach. Another approach is not to have it bonded. It's okay. If it's not bonded, then the liner will contract when you cool it down, and it's going to cause a gap between the composite and the liner. So one more time, let me repeat one more time. There's two types of design you can encounter, many others, but one is where the composite is bonded to the liner, and another one where the composite is not bonded to the liner. So since the composite is slightly has not cured yet, when you bring it to hot temperatures to cure it, the liner isn't there as well, and so the liner is going to expand while the composite uh, may not expand as much. So the liner may push into the composite a little bit. Once the composite hardens, the liner in the already expanded state will now, you have to bring everything now to room temperature. So the composite will kind of harden and stay in that same shape, which is slightly higher diameter, while the liner will cool down to a lower temperature. And so both will cool down to a lower temperature, but the liner will contract relative to the composite because of the cool down. However, the thing to point out there is if it's bonded, then the liner cannot contract as easily. So you're going to develop a state of stress between the liner and overwrap if there's a bond. And if there's no bond, then you're going to create a gap in between, potential gap. Not all designs have that issue. Okay, so I hope you can kind of pause for a second, think about what I just said. So what I'm trying to do with what I'm calling autofrettage. Don't worry about the word itself. Try to understand the mechanics of what's going on. So after I post cure the composite, so I've gone through cure. The thing is at room temperature now. What I'm going to do, I'm going to take that composite overwrap pressure vessel, and I'm going to subject that composite overwrap pressure vessel to a pressure that's higher than you may experience in service, and that's done on purpose. And you do that so that the liner yields. If it's a metal liner, it yields on purpose. You're doing that on purpose. You're actually yielding the liner on purpose. And that's going to cause the liner to plastically deform and expand. Okay? So let's think together about the physics of what is going on for a second. So step one, I increase the pressure, and the liner and the overwrap move together, outward. And they're probably in contact at this point. But now I plastically yield the liner on purpose. And that plasticity that I'm inducing into the liner is causing permanent deformation into the liner. Think about that. Now, the composite is a linear elastic material, and of course has a limit, typically 1.4% strain. But the idea there is that the liner now has permanently expanded. And so now what I'm going to do is remove the pressure. And what I want you to think about is what happened there for a second. Because when I apply pressure initially, the pressure in the liner develop a tensile state of stress. Think about that, right? Because I'm applying pressure. But now that the liner wants to stay in that position because I permanently deformed it. So when I remove pressure, the overwrap wants to return back to where it was initially because it's a linear elastic material. So that overwrap is going to push the liner so that the diameter of the liner is pushed to decrease. But it can't because it can, but not a lot, because the liner has been permanently deformed. And so what that's going to do is going to induce a compressive strain into the liner. So it's going to induce a compressive residual strain in the liner, and the idea there is to improve its fatigue life. I'll explain it one more time. Both of those processes really quick. I have the cure process, and the cure process, I heat it up, and the coefficient of thermal expansion is such that the metal typically is higher CTE than the composite. So when I heat it up, the metal will expand a little bit compared, not a lot, but compared to the overall will be. And then when the composite heats up and hardens in the hot state, because that's how thermostats work, then at that point, when I cool it down, the composite wants to stay there. The liner wants to cool down because it's a metal, and composites have lower expansion and contraction rates. So when I cool it down, the composite doesn't even care. The liner wants to contract. But now the thing is that if it's bonded, then you're going to induce a state of stress at that bond line. And if it's unbonded, which there are designs that are unbonded, then a gap could form potentially. And then I cover the idea of autofrettage, which I think is a new concept to you. Here, what I'm talking about is I'm applying a pressure now on purpose that's higher than the operational pressure. And I do that on purpose to the point that it yields the liner on purpose. I'm permanently deforming the liner. The overwrap is linear elastic, so it doesn't care. And when I push the liner, so it overwrap, it's expanded. The liner is in contact with the overwrap. The liner is permanently deformed now. When I remove the pressure now, the composite wants to return to its original shape, but it cannot because the liner wants to stay where it is. So that induces a compressive strain in the liner, and that helps with the cycle of life performance of the liner. Why? Let's think about that. Now there's a compressive strain in the liner. Think about that. It's in compression in the hoop direction, for example. So when I apply pressure next time in the vessel, now there's some compression that needs to be overcome before I hit tension again in the liner. So that means lower stresses in the liner as a consequence of having compression stresses to begin with there. So that's going to increase the fatigue cycle life performance of the liner. That sort of summarizes the idea of autofrettage in the curing process. I want to clarify. So we do the cure operation is required. You have to cure it by applying hot temperature. That's required to harden the composite and the epoxy particularly. And then we follow it with an autofrettage. So again, the post cure this cure operation is for the composite, is targeting the composite. The autofrettage is targeting the liner and it has a specific purpose, and that purpose is to increase the cycle life performance by inducing a compressive set of stress in the liner. And pictorially here, we're showing what's going on with the COPV, what's happening with the composite and the liner. But basically, already discussed what's going on verbally. The composite behavior is linear, so it just goes up and down. No problem there. It's linear, so it's going to go, um, to a out of frottage level and then come back, right, linearly. But this one here is different. The liner stress is going to go into compression after out of frottage, and that's the key there. And the next time you cycle it, is going to have less stress as if you had not done the out of frottage. So it's a little trick. It's kind of weird. A lot of applications, structural applications, you try to prevent yielding. Here, you're doing it on purpose, which is mind bending. So what are the composite failure modes you could have? So one of them is basically overpressurization. One possibility is that the fibers break off and the whole thing blows apart, and mostly because the fibers were not designed properly to take the load, and so the fibers will break. Fatigue failure of the metallic liner is an issue that can happen, and that's why you're trying to create the autofrettage. The fatigue failure mode of the metallic liner is mitigated by inspection and testing typically. You do non-destructive inspection of the liner at the manufacturer, so you want to do an NDE to ensure that critical fly sizes are adequately screened. The COPV design may be then pressurized, cycle tested during qualification, and I'll show you some of that later, to a factor significantly greater than the design life to ensure an adequate margin on design cycle life. The burst test, the burst thing I talked about here in the first one, ways you can prevent is really getting a good material allowable. You also want to do, after you build one of these things and you go through autofrettage, you want to do a proof cycle. What is a proof cycle? So say that the pressure in flight is 5,000 psi or 10,000 psi for that matter. You will then proof test it. What that means is I'll apply a pressure into the COPV that's greater than 10,000. And the purpose of that is to exercise those fibers beyond the flight conditions to make sure that the workmanship of that COPV is good enough. The external pressurization source must also be controlled to prevent accidental excessive pressurization. So you have to make sure it's a good test and everything is good. The burst resulting from metallic liner composite damage, failure of the composite can be mitigated, and it can be mitigated by doing a lot of damage tolerance testing, visual inspection. We'll be covering damage tolerance later in this course. Surface damage, composite materials are sensitive to surface damage and things like that. So you have to really pay attention to those. And if you have any amount of impact damage, you could have some subsurface damage. What I mean with subsurface damage is that visually in the outside you don't see any damage, but beneath the surface, the liner could have buckled, or beneath the surface where you cannot see anything, perhaps some fibers beneath or the delaminations are formed, something has happened. You also have the idea of stress rupture, where if you have, say you have a COPV that's subject to 10 years of pressure consecutively. Well, obviously, you're going to have some amount of potential for stress rupture. And so that has to be looked at as well, because stress rupture is really a situation where composite experiences a strength reduction due to the fibers being exposed to stress over a period of time. That's why. Um, And so that's something that has been researched quite a bit and looked at. Buckling of the liner can be a possibility. Usually the liner is thin, so this liner is fairly thin compared to the composite. And because I told you already, the liner is on the compression because of the autofrettage cycle, you could have a situation where if there's a debond, or if it was was unbonded on purpose, that the liner could buckle because it's under compression anyway. Another failure mode that people look at is the leak before burst. Liners are designed so that there is a leak before burst. What I mean with that is that if there were to be a crack in the liner, it will propagate in such a manner that the whole vessel will not explode, rather that there will be a leak that occurs at a not control rate necessarily, but it will leak before the whole thing blows apart. And that's the idea of leak before burst. The question is how to handle potential for temperature changes to this structure. So there's potential that this spacecraft, if this is used in a spacecraft, that the wild temperature swings in space could affect the COPV for performance. And so one of the testing that needs to be done anyway is a thermal cycle test to demonstrate adequate performance of this type of vessel. So here is the LBB failure mode kind of described now. So if this is a liner, you're typically looking at, if this is a thickness of the liner, you're looking at putting a flaw within the liner that's 10 times the thickness, and you're putting it in the length direction. So for example, I put a crack right here, 10 times the thickness. And the idea is to show that any pre-existing flaws in the metallic liner will grow through the liner, and it will result in a pressure relieving leakage rather than the whole thing blowing apart catastrophically. And so the idea then is to demonstrate that what people have come up with in industries to analyze 10 times the thickness of, you basically put a flaw that does not exist. You're doing it just to make sure your design passes this. That's 10 times the thickness. And you're doing that analysis. I will explain later on in this course how to do fracture mechanics analysis. So we're good there. Um, and you could do testing also at the subcomponent level, like a coupon level test. You don't have to do it in the whole COPV. But you could do analysis as well. People have done it. And then there's this idea of safe life or damage tolerance. What are we talking about there? So when you manufacture metals, and we have several aircraft applications where you've seen, for example, Southwest Airlines had a failure of the metal casing, fuselage casing, right? And that was caused and instigated by fatigue. Well, very similarly, there could be a crack that's probably not even detected. You may not be able to see it. That's within the liner, and that crack could grow over time. So, what the safe flight requirement is intended to do is to ensure that you can demonstrate 4 times the service life with the initial crack in a very critical orientation, but that's to an inspectable level with a 90% probability, 95% confidence that you'll find that flaw. So if I say, okay, I can find this point, 1 inch flaw with 90% of the time, I can find that flaw 90% of the time, 0.1 inch, with 95% confident, then what you want to do is perform a test program that puts a flaw, and it could be analysis. If you put a flaw that then exercises that flaw 4 times the service life. And when I talk about service life, what I'm meaning is every COPV is going to have, for example, the autofrettage cycle, a proof test cycle like I discussed before, but say the proof test, something went wrong and you have to repeat the proof test. After the proof test, you have to do the leak test and say that you have to do more and more cycles later during operation. Well, your service life has to account for all those operations, including thermal cycles. And you have to slap a factor of 4, and that factor of 4 is intended to account for the fatigue variations and scatter factor that exists in metals. Coupon and COPV testing are allowed. You can do testing, and there's a range of flaws you have to analyze for. So from 0.1 to 0.5 of this ratio, you have to kind of basically look at. So this A over 2C is a ratio that describes the characteristics of the flaw. 2C is the length on the surface, and A is the depth. And so you want to analyze that ratio of flaws to show good for safe life. These are the ideas that people have used to look at inspecting COPVs. Here's a thermostratigraphy idea. In a COPV, if there's a D-bond, you can see these. If there's circular D-bonds, you can see them using chirography. People have used vacuum chirography, but pressure chirography has been a good approach. COPV inspection is looking for fiber bridging, porosity, liner to composite these bonds, boss fitting these bonds, cracks, broken fibers, and impact damage. There's also variability in COPVs. COPVs demonstrate a large amount of variability in burst pressure and stress rupture progression rates. The NDE process have to be integrated into the manufacturing to reduce that variability and improve quality. NDE can often be applied at each major step from fabrication through qualification by targeting following areas of concern. You have to look at crack and grain boundary issues during liner spinning, weld flaws after welding, bridging during winding, liner to composite adhesive D-bond. We talked about that, where the liner and composite meet. If that's bonded, any D-bond could be a problem, because now, since the liner wants to pull away from the composite when it's not pressurized, then, and also after cure, then that's going to cause some amount of stresses there. If you cool it down even further, because say you have a COPV operating at cold temperatures, that'll make it even worse. And if a flaw exists, now you're putting a lot of stress concentration on that flaw, and that can result in a failure event, not catastrophic, but into a leakage event that could degrade the capability of the system. The areas weak areas for composites occur due to poor wetting or outgassing during cure. You can also have growth of pre-existing flaws during autofrettage, because autofrettage is a stressing condition. No pun intended, stressing condition. Creation of new flaws during autofrettage, excessive fiber breakage during autofrettage. These are some of the things that can go wrong. And liner buckling issues after autofrettage. So what are the typical tests we're looking for in a COPV? We have the proof test, which is an acceptance test to verify workmanship, a leak check to verify there's no damage, a qualification test with vibration included to look at scent environments, but also make sure we're qualified properly. Safe life test, damage tolerance for the liner, I discussed that. Pressure cycle test, I discussed that to check the fatigue performance. Burst test to ensure a robust design. You'll take that pressure at proof level and increase it onto the burst. And it has to meet a requirement I'll show you very soon. Impact damage tests that are followed by burst tests should be done. So if you have potential for impact damage and you don't have good ways to apply protective covers or something that protects the COPV from manufacturing floor all the way to the launch pad, then that can be a cause of concern if there's an impact damage event. If you don't have those protection in place, then you have to do more work to protect hardware. And then there's other types of tests in other standards, like gunfire, somebody shooting at a COPV, heating, things like that. And this is a standard that's used in industry, SO81B. It's a standard for composite overwrapped pressure vessels. So this is the AIAA SO81B standard. It's a standard developed for composite overwrapped pressure vessels. And I won't go through the details of this because you can download it from the library. And also there's a copyright statement, so we want to make sure we respect that. But I want to walk you through the main things this standard talks about. It talks about the general design practices, systems analyses, defining the maximum expected operating pressure, which is important, looking at load, acoustic shock, surface life definition, how clean the system is, fluids, and so forth. Then you have design parameters looked at, like the burst factor, design burst test, proof pressure, margin of safety, and mass design, and so forth. So, and then you're going to have damage tolerance, leak before burst, and fatigue design, and stress rupture. So those are key areas. Then you have stability verification and fracture control. And then you have a number of analysis requirements in there. The document then goes on to the manufacturing, quality assurance, verification by test, and so forth. And so my intent is kind of like skim over it so you can see what's in there. It talks about operations and maintenance, for example. And so this document has people from industry, different areas in the industry here. It has, here you have Scott Forth, for example, very well known in the area. So these are the committee that worked on that from a lot of different organizations. You can see that a lot of thought is put into this, and it's not just taken lightly. Um, and so moving really quickly because you should be able to download this. Point here is that the proof test tends to be 1.25. Sometimes NASA uses 2.0 for the burst test. So basically take that sample and take it to failure by pressurizing it. Well, the design is going to be, the proof factor is going to be 1.25, and then it can vary anywhere between 1.25 and 1.5, depending upon what burst factor you design for. So you can design to 1.5 and then use a proof factor 1.25. If you design between 1.5 and 2, use this formula. If it's greater than 2, you can still use this formula and you still get 1.5. So yeah, there you have it. There's a number of requirements here on damage tolerance, how to go about it, but I won't go into the details of that, other than to point out that there's a significant amount of material you can go and review through the library process. So the DOT standard, the Department of Transportation standard, also has a COPV standard there, and it goes into a lot of different stuff. Design qualification test is very similar and comprehensive as well. You also have the international standard, the ISO standard, that also has a lot of requirements similar to what you will see in the DOT or the AIAA standard. The European agency also has a requirements document that goes into the COPVs as well. That's worth highlighting to you guys. And there's an analysis code called the Abacus Wound Composite Modeler, which may not be available in the latest versions now as they move on. But the important thing is that this model can define the liner, can define that. It can produce symmetric or unsymmetric winding patterns. You can have to tackle polar boss, build up controls. It takes care of autofrettage and other things. So it's a good paper to look at. I also read a paper on how to analyze uh, composite overwrapped pressure vessels with particular scenarios of delamination near transition zones between the dome and the composite. And in that paper, we're providing a systematic approach for conducting a finite element analysis. And that analysis has been automated using an in-house code. And that code, basically what it does is tries to understand, execute an analysis that can help you understand the stress states so you can make a better decision in the design. So if you were to do an abacus model, you will have input data for the COPV, geometric data, winding pattern, composite data. That goes into an abacus input deck, and then you can perform a autofrettage cycle, multiple proof cycles, and operational cycles to study the liner behavior, and then you can do post-recovery to look at ply-by-ply stresses and other things. And here's a typical approach. You may use an autofrettage to 1.3, a proof test to 1.25 subsequently, which will be less stressing than this one because this one pushed the boundaries of the liner. And then finally, yeah, you have your MEOP, which is 1.0 MEOP. Typically, the modeling is done axisymmetrically. It saves time. So continuing on, these bounds tend to be done axisymmetrically in abacus, for example. And the key here is, and you'll see that in the paper when you look at it, that the ply angle varies from one end. So this is the polar end, this is a cylinder, right? And so that angle is going to change from here to here. Not only that, the ply may end at some point in the dome, and also you're going to have a ply stacking sequence. So it's a very complicated analysis. And so a lot of times a hand calculation is first done using netting analysis, which I'll introduce to you to. You can see here the cylinder and the overwrap with the ply dropping off. And you don't want to have too high of an angle in the dome section because the fibers will slip and then you will not have a good design. But the one composite modeler is something that used to be in Abacus. The facilitated model creation and the liner counter was provided for to do that. You will then provide this data, which clearly varies as a function of location. You have to put nonlinear stress strain curve, and you have to perform multi-step analysis that considers, in some cases, you have to even consider the cure, but you don't have to in every case. You can just do a nonlinear analysis starting with the autofrettage process to fully understand the stress states introduced into the COPV design. So a typical finite model relies on the liner geometry. You have to have that shape, that inner liner geometry, and outer liner geometry to understand its thicknesses. You also have to do the same with the composite and understand the interfaces between the liner and the composite. The winding pattern is extremely important. That tells you how the thing is built using a filament wind machine. And that's why it's important that we look at that from the pragmatic point of view. All the disciplines should be looking at that. Okay, from the Abacus manual, really quickly, a number of different geometries are available in Abacus. For example, you can look at the dome geometry, plug in, and it can allow you to look at the wing angle definition. You also have to look at the geodesic dome idea, which is a specifically shaped dome which results in a constant strain state along much of the fiber as it wraps around the dome. Not every dome is geodesic in nature, but it's something to highlight. The manual also discusses some of the things they did with the buildups, the helical layer buildups. Here's another paper that's worth reading that talks about the analysis of potential for titanium liner buckling after proof in a large Kevlar epoxy COPV. So here the fiber is not carbon, is Kevlar because it was needed for a impact damage resistant calculation. And this paper goes into a lot of aspects like the Bauschinger effect, talks about yielding, talks about holding the proof at a particular level, and things like that. So I'm going to go ahead and play a couple of videos on this topic by somebody I respect very much, Lori Grimes Ledesma. Enjoy.
My name is Lori Grimes Ledesma, and I'm at JPL. I've worked COPV technology off and on for about 18 years. I keep thinking that it's going to be finished up any time now, and in 18 years, there's been quite a bit of work in this area. I've been very surprised by that. Composite overwrap pressure vessels, or COPVs, have some significant advantages over all metal pressure vessels, which we used in the 60s and 70s on all of our launch vehicles and human spaceflight vehicles. And they also have some disadvantages as well. And so the technology really has to be carefully used. There's got to be a lot of oversight and review of pressure vessels, or actually of COPVs, as they are being manufactured and designed. The advantages of COPVs are that you can reduce the mass that's used to store your gases. or propellants or any other kind of fluid. So by doing that, you can save up to 50% of the mass over, say, an equivalent all-metal pressure vessel. That leads to significant advantages for overall spacecraft weight, because spacecraft or launch vehicle weight, actually, because usually you need more than one. There's usually multiple pressure vessels. That can add up to a lot of weight. So that's really the advantage of using COPVs over all metal pressure vessels. The disadvantages of COPVs are that it's a deceptively complex structure. There is a metallic liner overwrapped with a composite material, and they function together to contain the gas inside or the propellant inside. And there are relative loads that go into the liner versus the overwrap. The entire thing must function together, and so the relative contributions of the liner and the overwrap have to be understood really well. And also, all the failure modes associated with each, with both metallic and composite materials, have to be considered in the design. So one of the inherent risks of COPVs is that they are a high energy storage device, and so that can lead to significant risk if it's not handled correctly. So for example, for a pressure vessel that is 1,300 cubic inches with storing, for example, helium or a gas at 9,700 psi, that is equivalent to 3.6 pounds of TNT. That is a significant energy that is being stored, and if it is not appropriately handled, then that can lead to a significant risk for a spacecraft or a launch vehicle. Some of the significant failure modes for COPVs are both liner and composite related. So the liner failure modes that we've actually had failures occur during flight and also during qualification have been things that are associated with fracture control. So those can be things like sustained load crack growth, stress corrosion cracking, cyclic fatigue type crack growth, incompatibility with the fluid that's being stored within the COPV, buckling of the liner. For the composite, there's other failure modes. Those can be in some ways more insidious because it is sometimes you don't get notice and they're very difficult to model. So for example, those could be impact damage that's non-visible. It could be stress rupture failure mode, which can occur regardless of the type of overwrap you're particularly using in your composite. And those are particularly significant for COPVs. So, for example, for the shuttle, when they were doing development and qualification of COPVs that were specifically going to go on the shuttle, they had 9 failures that were both for metallic pressure vessels and also for COPVs. Those were related, and so that's why I mentioned the all-metal version. Those COPVs failed from a lot of things that we deal with now using fracture control. So stress corrosion cracking, weld pores, weld defects, weld cracks, also cyclic fatigue. A lot of these things occurred because the Ti-64 that we were using at that time was kind of new, relatively speaking, and so we weren't terribly confident in our ability to weld. since then, there's been a lot of advances. But at the time, these failures were occurring because we weren't, the technology was still a little bit immature at that time. In addition to the failures that occurred for shuttle during the development phase, since that time, we've done a lot more looking into COPVs in general and understanding how they fail. One of the failure modes that has become important is stress rupture life. And that stress rupture is the sudden failure of a COPV at typical operating pressures. And we know that this occurs, and we can make this failure mode occur in the laboratory. Fortunately, it has not occurred on any flight project, but it could. And we need to understand the bounds at which it becomes important. That failure mode is, we know that it exists from test, but we aren't aware that it's, we haven't seen any failures due to that in service. Mitigation for failure modes of COPVs, a lot of that comes out of adequate and careful design and qualification. So a lot of things in the design we have to take into consideration our understanding of exactly how the COPV works. What is the pressure load that's going to be put on the liner and overwrap? Do we understand the relative contributions of the liner and the overwrap? And do we understand all of the different the load environments that COPV is going to see? Making sure that all of that is incorporated into the initial design and analysis phase then supports what we do for qualification testing. Adequate qualification tests for cycle life, for proof test, for autofrettage, for vibration test, making sure that all of those are adequately done, and then providing sufficient oversight to make sure that everybody who is working on and trying to understand the amount of risk that is associated with a particular COPV design understands all of the design and tests that have been done to help prove out that COPV. If during the flight phases there are any changes to the pressure loads or the number of cycles that a COPV is going to see or the amount of time it's going to be under pressure, all of that stuff needs to then be revisited with respect to the design and qualification approach. So in addition to the design details and the testing of the qualification tanks, the manufacturing steps involved at a specific manufacturer will need to be understood, and any deviations from sort of a typical and assumed approach for the fabrication of the COPV need to be understood and maybe even incorporated into the design, depending on what how varied it is. In addition to that, another concern for COPVs and a significant risk to the composite is impact damage. And so this is where a COPV gets impacted during either in the factory during manufacturing or during transportation to the facility where it's going to be incorporated into the flight system, or even after it's been incorporated into the flight system, to make sure that there is no possibility of the composite being impacted after it's installed. Mitigation of impact damage to the composite is all done through process control. There is not, that can't be necessarily designed in per se, although you might be able, one option is to test to a particular impact level and say, okay, well, I actually achieved my initial burst capability, but most of the time, process control is put in place just to make sure that the COPV is going to be what is expected. It's going to perform as expected once it's in the flight system. And so things like impact damage control plans and the incorporation of impact damage mitigations into any installation procedures for the flight system, and then anything that could occur to that COPV afterwards, all of those risks should be considered in the damage control plan. Factors of safety that are currently in COPV design standards are used, and those are used in order to prevent any kind of overpressure or strength failure associated with the COPV. Those failures are extremely rare because the design, you're required to do finite element, and then you're required to prove out the strength of your vessel through a robust qualification approach. Another area where risks are mitigated during the design and qualification is for fatigue crack growth, for example. And in that case, COPVs are inspected, the liners are inspected using typically dye penetrant or X-ray radiography to determine if there are any cracks and to establish an initial crack size. Then that there are either analysis or tests that are conducted to understand whether or not your design or your liner is actually robust to cracks. Going forward, I would say probably the three most important failure modes for COPVs for very long missions going to Mars or just for extended stay in space. I would say for COPVs, I would want to watch liner fatigue crack growth and crack growth mechanisms, impact damage, and then also stress rupture mechanism. Make sure that those three failure modes are completely understood. And one thing about that is very careful, detailed-oriented work needs to occur during the design and qualification phases of a COPV in order to make sure that we can fully understand what the risk of any of those three failure modes would be. I would just say that the failures that have occurred in the past and some of the lessons learned from either the Apollo or shuttle, all metal tanks and COPVs, one of the really key things and something that's very important is to look at something that's perceived to be the small stuff. Some of these failure modes, or these failures, in fact, that we've seen in the past, have been due to things that we thought were okay, or that's probably okay, or there's I think that we don't need to worry about this small detail. But really, these seemingly small details are very significant, can be very significant, and the COPV is susceptible to failing as a result of oversight of some small detail.
So we're gonna watch a little bit of a video of a
A
test.
vessel test of the Orion ascent abort component. This tank was tested this year to determine if it was susceptible to mechanical damage for the credible threats that were identified during operations. So the vessel is being pressurized after mechanical damage at the visual damage threshold to see what the residual strength of the component is. You can see some strands breaking as damage progresses through that tank composite, and the tank is pressurized with water, so it's hydraulically pressurized. In service, it's pressurized with gas, with nitrogen. So it's more than an order of magnitude more energy in actual service. The energy in this case is below 1 pound TNT energy equivalent, and you can see the damage there, and there's nothing left.
So one of the
Hi,
areas
my
that's
name's Nate
key,
Green, NASA White
one of the
Sands
areas
Test.
that's key here is really understanding the fact that composite override pressure vessels can be quite susceptible to impact damage events that can be quite damaging. And so it's important to really figure that out very well. I also want to point out there's non-destructive evaluation working groups really developing approaches for practicing how to find flaws, uh, detect flaws, defects, and accumulated damage in COPVs. In general, we know these vessels can be very, very small thickness, 90 mils or 0.090 inches, and that you could have quite a bit of issues, particularly with impact damage. And so the idea is to really quantify all the damage threshold, all the damages you could potentially have in a manufacturing facility, and try to incorporate those damages into the test article, and then test it to show that you can survive those loading conditions in practice. If somebody were to drop a tool, for example. There's also standard practice on how to apply geography for COPVs, or filament one pressure vessels in aerospace applications. A very good document to look at. I also encourage you to look at hand calculation sizing, how to size pressure vessels using a book such as this one, the Composite Filament Winding Book, as an example. So I'm going to kind of go over very quickly from the books from Peters, 2001, the approach that's used to, what are the equations that are used to really analyze basically pressure vessels with composites. And the approach that is really used is called the netting analysis. And it's a really simple process. And the idea is that you can use that netting analysis to predict stresses in the fibers. And what you're doing, you're neglecting the contribution of the resin. And the procedure is quite simple. It's almost based on free body diagram. And the technique is really applying just static equilibrium. You're not looking at anything else, and you're not even looking at flaws. And the idea is that you can size the design using the simple equations, and it's usually used as a first order estimate, and then later on you can do a finite element analysis that counts for that. Um, if I were to take a pressure vessel and I were to have a radius, and it had a radius r, and it's subjected to internal pressure pi, say as an example, and I had angles at fibers. The fibers are helical fibers at theta, and an angle theta relative to the axis of the COPV, and the allowable fiber stress was sigma f theta. So allowable fiber stress, what I mean with that is that's the maximum stress that I need to design to, or the lowest stress I should design to, like an A base is allowable. And we already covered how to calculate A base is allowable and B base is allowable in the previous course. But I'll refer you to that lecture on how to calculate A basis, or any of my composites course YouTube videos as well. And the idea is to, okay, how I determine the thickness of the fiber and the wind angle to really get a good design. So if I look at the if I look at this, um, I'll look at this figure here. I can do a cut. So I have a uniaxial cut. That's your line load NX, and that's going to get react. It's going to react a load this way and this way. So I have fibers going that way and fibers going that way, right? And if I do a cut like that, then this load NX is getting equilibrated by the load going that way and that way. And using geometry, you can determine what is the load that needs to equilibrate NX. So that's what you're looking at there. I encourage you to pause the video and kind of look at how that was done in terms of geometry. It's very simple, right? This is cosine theta right here, and that's cosine theta. So that should be fairly simple. And so then I can then perform equilibrium, and since I have two of these, then I get a single one of them. So I have the stress, the allowable fiber stress, times the thickness, fiber thickness, times cosine theta squared, cosine squared theta. Okay, so that's what I have, and that is going to be equal to, so the axial force is going to be equal to PIR over 2. Now, you can see here that there's no T. You're used to seeing stress equals PR over 2T. But again, this is a line load, and so therefore there's no T. So that's why you see that. So you can solve the equation for T, and then you get this equation. And then you can sum forces in the circumferential direction now. So that's this diagram here. So you can basically add forces in this direction. We added in this direction, but now we have to add in this direction. And when you do that, instead of this equation here at the top, you're going to get this equation at the bottom. Now remember, the longitudinal stress is PR over 2T, the stress. The line load is PR over 2. P is the pressure, R is the radius, theta is the fiber angle, T is the thickness of the fiber, and or the lamina, and sigma f theta is the allowable stress I'm designing to. So I can solve for T there, and then I can repeat this process, but now in the hoop direction. Now you can see this stress here, N, or line load N, is PR only, not PR over T, again, because it's a line load. So then adding forces in this direction now will then produce this equation here at the bottom. Okay. So using equation 5.62 here and 5.63, I can then look at that and calculate a ratio. So I can basically calculate a ratio if I wanted to. And that ratio comes out to be 54.7 degrees if I take that ratio. And I find that theta is 54.7 degrees. And this is the wind angle that is required for a pressurized cylinder with helical windings only. But a vessel is going to have both 90 degrees and 0 degrees. So not 0 degrees, but it's going to have lower angle degrees. And so as a consequence, you want to look at other considerations. So if the vessel is wound with both plus minus theta, so I have angles at plus minus theta, and I also have 90-degree fibers, we want to determine how much I need for how many plies I need for the ones that are helical, and how many plies I need for the ones that are 90. So you can actually use the same equations I just discussed, and what you will find is that that'll produce this equation right here, where now I have a relationship of, if I know the fiber stress in the hoop direction, and I know the angle theta, then I can calculate the thickness of the ones I need. Um, yeah, the fiber thickness in the theta direction. Um, so yeah, that's kind of the process that's typically used. This is some other information on cross-sectional area of typical rovings for fibers. Um, and you can basically calculate basically uh, the thickness for the fibers going in the theta direction and the thickness for the ones going in the 90 direction. So let's look at this numerical example really quick. So we're going to use the equations above to figure it out. And so I want to basically design a pressure vessel and I want it to survive 6,600 psi burst pressure, has a diameter of 5.75 inch, and the winding machine is set up to be 0.23 inch hoop bandwidth and 0.2 inch helical bandwidth. Okay, so that's what we're talking about there. The specified helical wind angle theta is 12 degrees. The vessel is to be wound using Kevlar 49, which is very typical. And that was similarly used in the shuttle program. Design allowables will be 425 KSI hoop fiber stress and 320 KSI helical fiber stress. These numbers typically will be about that actually in a lot of design situations. And then they're asking us to use a translation efficiency of 77% for the hoops, 58% for the helicals, and 75% ratio of helical to hoop fiber stress. I'll discuss some of that a little bit down the road. So now I can calculate the helical fiber thickness using the formula that I have just above here. So I know the pressure is 45. This is in megapascals. I know the radius, which is 5 points. Well, so it's 146 divided by 2. So that's going to be 73 right there. Then I have the 2 there. And then I have for the helical fibers, the allow is 2.21 gigapascals, hoop fiber stress. So I put that there. And then the angle for the helicals are 12 degrees. So that gives me a thickness of 0.79 millimeters. And yeah, so I know it's 0.79 millimeters for the thickness. If I assume there's 3 layers, I can then determine basically using the cross-sectional area roving. So I know it's 0.352 for that. So I put the cross-sectional roving area here, 0.352. And then I can calculate based on the fiber volume fraction, or the weight fraction. I know the thickness is 0.79. And then I can calculate now the number of plies I need. And I get about the number of helical spools I need is 2, basically. So yeah, so that's kind of like the typical process used in this example problem. Um, and then you can calculate the required hoop fiber thickness using the formula I discussed earlier. Um, and we'll get 1.11 centimeters. And then I get, if you assume 9 hoop plies, the number of hoop spools will be 2 using a very similar approach. Again, this 5.8, yeah, so we're using the typical fiber volume fractions to calculate it. What else we got? So that'll be about it for that example. So these paper, an analysis of composite pressure vessels. Like I said, I have one that you can look at, and here's a different one. This shows the modeling that was done in ANSYS, but very similar approach. Again, you're ignoring the effects of the liner. You're just really sizing, really for the structure. And so here you can see the cylinder again, the line load going that way, the line load going that way. You can do a cut this way, a cut that way, and do equilibrium. For a pressure vessel, N theta is P times R. That's a line load. N phi is PR divided by 2. That's a line load in the hoop in the axial direction, while this one is in the hoop direction. P times R is in the hoop. PR divided by 2 is in the axial direction. Very similar process. Now here, what I like, it shows the factor of safety, so it's kind of cool. I have the allowable design stress, so I know the ultimate value of this fiber system divided by factor of safety gives me an ultimate strength, and I want to design to that. So I can then calculate the thickness of the helical portion, and I do that with this formula. I plug in the sigma ultimate here. I know alpha, and I know n theta, so I can calculate the thickness. For the 90-degree ones, I use this formula here, um, right here, and then we can determine using the fiber volume fraction. Typically, the fiber volume fraction will be in the 70% range. So you can calculate the total thickness of the whole thing by using this formula. I take the thickness of the helical ply angles plus the 90-degree ply angles divided by 0.72 gives me the total thickness for the whole thing. Then I can calculate the number of helicals in the hoop in helical directions using this formula. So I know the thickness divided by 0.72 times t, and I calculated t, so I should be able to calculate the number of hoops and helicals. Okay, and the rest of the paper goes into geodesic contours, which I encourage you to look at more carefully. That's basically how to, and it has even an example here, a very specific design example um, that walks you through with formulas. I encourage you to pause the video and or just look at this carefully. All the information is provided here, the steps that are needed to analyze this. But this is something that you encounter, and this was compared to ANSYS, and it did really well. I mean, it was not too bad. The bottom line is that their design tools are used as initial sizing, then you make it more accurately later. You know, I like this book as well. It's called the Composite Filament Winding Book. And it actually goes into a lot of the details I already discussed, including the CSA, the roving area, the cross-section roving area. Uh, and it goes into more details about how you will even consider moment. You could consider moment as a potential effect. And so it's nice because you can, the previous examples I was showing only included pressure inside, but you could have moment, for example, acting in the COPV, or some other stuff acting on the COPV. And the formulas, again, are very similar. You can see the formulas are very much the same. Nothing's changing there. Um, and yeah, so generally speaking, it also has a very nice example towards the end, a design example that explains the process on how you design it. It also provides some sizing for the dome contours, how you address the contour location here. And the formulas there become a lot more complex, but it is very doable. With a good software, you should be able to go through that. A lot of companies already have a lot of these formulas really used, and it shows the design approach typically. Like this book will show the design approach. It will talk about stiffness, the types of discontinuities you can have, the kind of stress ratios we're looking for. Is going to have information on skirt design and other things that are quite interesting. So I encourage you to kind of look through that and kind of gain an understanding of this material, which I'll make it available to you. But uh, generally speaking, the COPV design process is fairly straightforward. The hard part is to do the analysis for the liner, the fracture analysis for the liner. The burst testing is done, and you know I trust the testing more than analysis. So, and a lot of this design, you're going to accept the design based on the testing, not the analysis. The analysis is a tool to help you get 99% there so that you can increase your success in passing all the different tests. The fracture testing, the impact damage tolerance testing, all those tests can probably be done with higher accuracy through the test program and not analysis necessarily. But again, analysis is still important because you need to size the design in the first place. You can't do it without it. So, with that said, I encourage you to read the materials for this book. and that you may learn a lot more about composite overwrap pressure vessels. And I hope you found enjoyment in a very challenging topic. It's a challenging topic that comes up